a circuit realized here using two ideal op-amps as seen. We want to prove that the current I1 at seen at port 1 is defined by the voltage at port 2 V2 over R as shown here, and then vice versa. I2 is negative 1 over R times V1. Basically, I2 is defined by V1. If we can prove this, then we are showing the circuit is a gyrator. Okay, let's make the assumption that the two op-amps are ideal, properly biased, not saturated, in linear region with dominant negative feedback. If that is the case, then I can write that virtual short is valid for both of the two op-amps, and therefore, because of virtual short, we are saying as long as the op-amps are in linear region, then the positive input terminal of the op-amp is equal to, has the same voltage at the negative input terminal of the op-amp for each op-amp. So let's name this relation 1. Now, the current I2 is coming in. Nothing can go through the input terminal of ideal op-amp because it has infinite impedance. I2 has to flow downward. That I2 goes down, and the same reason nothing can go through the negative input terminal. So I2 has to go through R. Therefore, if I name this node X and if I name this node Y, what I can write is Vx minus Vy is equal to the voltage drop across resistor R, which means R times the current I2 that is flowing through R. At the same time, from equation 1, I know that the voltage, the Vx minus Vy, is the voltage difference between negative terminal and the common node. Therefore, it should be the same as V positive minus common node. So Vx minus Vy should be the same as, because of virtual short, as V positive for op-amp 1 minus Vy, which is the common node there. It's a floating supply. So at the same time, now the nice thing is what is between the positive input terminal and common node is, as you can see, positive is connected to a negative terminal of input port 1, and the Y common node is connected to positive. So effectively V positive minus Vy is just negative V1. Combining these two, I get negative V1 equal to Ri2, or basically what I was chasing, one of the two equations. I2 is negative 1 over R times V1. I got one of the desired equations. Now for the other one, we need to observe an interesting property. Here we have a two-port shown here. And in this two-port, we can see that the current going in is 0, because nothing can go through the input terminal of ideal op-amp with infinite impedance. So the current coming out effectively 0. This I2 in a steady state, this I2 that is coming in through this resistor has to flow back through this supply point and go back to the op-amp. So this current is 0. Therefore, I1 comes in, and I1 can only go this way. So here is the current I1, and again, I1 cannot go through the input terminal of ideal op-amp because it has infinite impedance. Therefore, I1 has to go completely through R. And the interesting thing is, because I2 goes in, and here we have I2 going out, this I1 comes down, and then we will have the voltage drop across the negative terminal and common node. So let's name this, again, you can name this as Z, node Z, and node W. So what I can write is exactly what we saw before. I can write that VZ minus VW is equal to the voltage drop across resistor R, which is R times I1. At the same time, because of virtual short, the voltage drop between negative and common node should be equal to voltage drop between positive and common nodes. So VZ minus VW should be the same as V positive at 2 minus VW. So V positive for op-amp 2 minus VW, which, as you can see effectively, is just V2. Combining these two, I can see that V2 is Ri1, or basically I1 is V2 divided by R. So I proved the second equation, and therefore the circuit is really a gyrator. In summary, I can just say the circuit is effectively realizing, so is a gyrator, and usually the symbol for gyrator is shown this way. This is the gyrator, and we have I1 and plus minus V1, and we have I2 and plus minus V2. And basically what we are saying in the gyrator circuit as shown here, we are saying I1, I2 in a matrix format is equal to, we have 0, let's say in this scenario, we have 1 over R, and we have negative 1 over R. And we have 0. And then what I'm just doing is I'm just writing these two equations. I found equation number 2 and 3 as in matrix format. That's all I'm doing. So this is the gyrator matrix, and sometimes instead of writing it this way, people like to write it this way as well. So instead of 1 over R, they say G, and instead of negative 1 over R, they say negative G. And in this case, they would refer to it as gyration conductance. So G is 1 over R is conductance. So they refer to G as gyrator or gyration conductance. And R in this case is the parameter of gyration, which you can refer to as gyration resistance.